Okay, today we're just going to go through some more tricky integration problems. So this video is going to be on the premise that we already know how to integrate, and we know and learned some of the rules such as the reverse chain rule and integration by parts and substitution. Okay, so we're going to go through integration by parts. We're also going to look at some looping ones and the reverse chain rule, trying to integrate more difficult trig terms, and finally some substitution. Okay, so if we move straight ahead, so the first one we're going to go through is integration by parts. Hopefully by now we all know how to, or we are very familiar with this formula. So it's just a matter of just looking at some more difficult questions. Okay, so if we start off with something very simple, such as this x times the sine x dx. So when we do integration by parts, we generally want to try and reduce one of these functions into a constant. Okay, so in most cases, IU will be just x. Okay, and that means our v prime will be the other function, which will be sine x. Okay, differentiating IU, we'll get u prime, and that's just going to be 1. And our v prime, or that's just, sorry, our v, that's just going to be minus cos x. Okay, so if we were to look at this equation, just following this formula, our uv will be our minus x cos x, and we're going to have negative minus the integral of v u prime, so that's going to be minus cos x. There's a minus, so I'm going to turn this into a plus. So cos x times our u prime, which is just 1, so it's just going to be cos x, like such. Okay, so if we're to integrate this, then it'll be minus x cos x, and integrating cos x, hopefully we know that's just going to give us plus sine x, and then we have our constant plus c here. Okay, so starting off with something relatively simple, this is how you'd go about integrating this term. Okay, so if we were to look at something a bit more tricky, so for example, if we were to look at maybe x squared times ln x. Okay, once again, the difficulty is just trying to understand which one our u is going to be. And in most cases, we would put u as x squared, like such. However, if you look at this question, we have this ln x term here. So we can't really differentiate integrate ln x. So in this case, instead of our u being x squared, we're going to put our u as equal to the ln x. And therefore our v prime is going to be x squared. Right, if we're to differentiate our ln x, we'll just get 1 over x. And integrating our v prime, v, we'll get x cubed over 3. Using this integration by parts formula, we'll end up with uv, which will be x cubed over 3 ln x, minus the integral of v u prime, so it's going to be x cubed over 3 times 1 over x. Just integrating this part, well, we can simplify this, so it's going to be negative. We're going to be left with x squared over 3 dx, and that's going to leave us with the whole integral will be x cubed over 3 ln x minus x cubed over 9 plus c. Okay, so whenever you are met with a ln x term when you're integrating, always set that as our u. Okay, in other cases that we would naturally set x squared as our u, but if we have an ln x here, be sure to make that as our u. Okay, so that's some of the key points. If we're looking at a more difficult question, another difficult question would be this e to the 2x times sine 3x. Once again, it's trying to understand what our u is going to be, and it's not very clear in the very beginning what we could set u as. So let's just set u as our e to the 2x. And therefore u v prime, that's going to just be sine 3x. Differentiating our u, we'll get u prime, that's just going to be 2e to the 2x. And integrating our v prime, we're going to get negative 1 over 3 cos 3x. Following this formula here, we have our uv, so uv would be negative e to the 2x over 3 cos 3x minus the integral of vu prime. V has a negative here, so I'm going to put it as plus straight away. So plus the integral of v will be 1 over 3 times u prime, this is 2e2x, so 2e to the 2x over 3 cos 3x dx. Once again, we have two more functions of x, so we're going to have to do integration by parts again. So over here, let's set a u, let's set it as 2 over 3 e to the 2x, and v prime, that's going to be cos 3x, the other function. If we differentiate our u, we'll get 4 over 3 e to the 2x, and our v, well, that's going to be 1 over 3 cos 3x. Sorry, not cos, sine 3x. Okay, so applying the formula again, well, this term is going to bring down. So we're going to have plus uv, so that's going to be 2 over 3 e to the 2x times this v term. So straight away, that's going to be 2 over 9 e to the 2x sine 3x minus the integral of vu prime. So straight away, that's going to be 4 over 9 e to the 2x sine 3x dx. We're still left with two functions of x, okay? So this is what we call a loop, okay? So the integral is looping. So if we keep doing integration by parts, all we're going to do is keep looping and looping and looping. So what we should understand is, well, this term here is very similar to our original integral here, okay? So in fact, it's exactly the same apart from this 4 over 9. So if we were to label this integral, original integral, let's call this one I, like such, then this integral here, well, we can say it's going to be negative 4 over 9i. Because they're the same integral apart from this constant 4 over 9. Okay? So the reason why we do this is, well, because... Sorry. So the reason why we do this is because, well, the original integral we're doing is I, right? So our I is equal to all these terms. So negative e to the 2x over 3 cos 3x plus this term here, if we bring that down, plus 2 over 9 e to the 2x sine 3x minus this 4 over 9i. Okay, so that means if I was to bring this I, 4 over 9i, to the right hand side, okay, so if I were to bring it to the right hand side, we'll be left with 13 over 9i is equal to negative e 2x over 3 cos 3x plus 2 over 9 e to the 2x sine 3x. Okay, we just want to be left with this I, so dividing this whole term by 13 over 9 will mean we have 9 over 13 on this side, and we'll have this whole term, negative e to the 2x over 3 cos 3x plus 2 over 9 e to the 2x sine 3x, and then plus rc. Okay, so this is an example of a integration by loop, okay, because we're going to keep integration by parts and we're going to keep getting the same loop. So we just label it I and then rearrange for I later on. Okay, so whenever you see this, just make sure, just try and identify or see if it keeps looping or not. Right, so that's integration by parts. So we're now going to move on to a bit of reverse chain rule. Okay, so for the reverse chain rule, what we need to identify, or what we need to try and notice, are these patterns. Do we have the derivative times its function, or do we have the derivative of the function over the function? In which case, it's going to be one of either of these two formulas. So let's just try and see how this works. Okay, so the first integral is 4 sin x cos x over 10 minus 8 sine squared x. That should be a dx here. At first glance, it seems very hard to see how we're going to go about integrating this. But if we look carefully at this sine squared x term here, okay, if we look very carefully at this term, okay, Okay, the next integration we're going to look at is the reverse chain rule. So for the reverse chain rule, we want to try and identify one of these two patterns I've written up here. So either the derivative of the function times the function to the power of n, or the derivative of a function over that function is going to give us one of these two integrals, okay, the answers. So that's what we're going to try to find. So let's look at the first question here. There's 4 sin x cos x over 10 minus 8 sin squared x. At first glance, it seems kind of tricky and we don't know like where to start. But if you were to look at this sin squared x here, if we were to differentiate sin squared x, like such, well, using the chain rule, we'll end up with 2 sin x cos x, okay? And if you look at the numerator of this fraction, it seems to be very similar apart from this is a factor of 2 times by 2. So this is an example of the second equation here, or the second formula. Okay, we have the derivative of a function over that function. So what we can say is we can say let y equal to ln, this is going to be ln of the function. So ln, the function being the denominator here. So the whole denominator, 10 minus 8 sin squared x. The reason why we do this is because if we were to differentiate this y term, dy by dx, we're differentiating a ln term, we always get a fraction with this function always on the denominator and the derivative of this function on the numerator. So differentiating 10, that just disappears because it's a constant. And it's minus 8 sin squared x. Well, we differentiated this sin squared x earlier on, right? So we just have to times it by this negative 8. So we should get negative 16 sin x cos x, like such. We now go about comparing this dy by dx term with our original integral. And you can see it's very similar, apart from now it's the constants, where there's a 4 here and we have a negative 16 here. So we want to get rid of this negative 16 or reduce it to 4. So what we do is in our y term here, we just times it by minus or divide it by 4. So 1 over 4. That way, if we were to differentiate this now, we would get the same term as we got for the original integral. We are making the integral. Rather than trying to integrate it, we're trying to make the integral by differentiating. Okay, so the integral of this term here will just be our y term here plus our c. Okay, so the hard tricky part is trying to see, do we have the derivative over the function? If we do, then it's going to be some constant times the ln of the function plus c. Let's look at the different reverse chain rule questions. So let's take a look at this sec to the power 4x tan x. Okay. Once again, this may seem a bit tricky, but what we should understand is, well, if we were to differentiate sec x or secant x, we would get secant x times tan x. So this integral here looks kinda in this form, right? Okay, it said this is to the power 4, this is to the power 3. So I can rewrite this as secant x tan x times by secant to the power 3x dx. Okay, and as you can see, this is the integral of, or this is the derivative of this original function. Okay, raised to the power of n. Okay. If that's the case, then we know that we can say, or let y equal to this function, in which case that'll be secant to the power 3, but we add 1 now, so secant to the power of 4x, like such. Okay, and if we were to differentiate this function, well, we would get, using the chain rule, the 4 will come to the front, so first 4 times secant cubed x times secant x tan x. Simplifying this a bit, we get 4 secant to the power of 4x multiplied by tan x. And you should notice that this term we get and the term original integral term we have is very similar once again, except now we have this 4, which we don't want, so to our y, we divide it by 4. Okay, or times it by 1 over 4. So our final answer will be this y is equal to 1 over 4 secant to the power of 4x plus c. Okay. Right, a couple of other more trig terms to integrate using the reverse chain rule is these four. Okay, these four should be given to you in the formula book here, but just it's good to derive them. So let's go about trying to derive each one. Right, the best way we should do it is reduce this into sine and cos. Cotangent we know is just cos x over sine x. Okay, and this once again looks very similar to our derivative of the function over the original function. In which case we can say, well, let's let y equal to the natural log of sine x. Why? Because if we were to differentiate this, we'll get sine x on the denominator, differentiating sine x, that will be cos x, and that goes straight to the numerator. And this derivative term is the same as this integral term here. So the integral of cot x will just be our y value here, which is ln sine x plus c. Okay, all of these four have the same method. So once again, let's try this tan x. So tan x is going to be sine x over cos x dx. It looks very similar to its derivative of this original function. So we say let y equal to ln the denominator, cos x. If we differentiate this now, dy by dx, we'll have cos x on the denominator. Differentiating cos x will get negative sine x on the numerator. We now go about comparing our dy by dx term with this original sine over x term, and you can see that's just a negative sign, which is different. So this tan x integral is just the negative of y. So negative ln cos x plus the c. We'll look at now the secant term and the cosecant term as well. So secant, now these two terms are a bit more tricky than the cotangent and the tangent ones. So what we're going to do is, it might be very hard to identify what our y should be, okay? In this case, it's going to be the natural log of secant x plus tan x. Okay, this might seem very tricky, okay? But let's go about just showing why it's the case. Because if we were to differentiate this dy by dx, well, we know differentiating natural log terms, the function goes straight to the denominator, secant x plus tan x. And now we just have to differentiate this term here. Differentiating secant x, we get sec x times tan x. And differentiating this tan x term, we'll get plus secant squared x. This looks very messy, okay? So if we were just to like simplify this, well, they all have secant terms at the top, so we can factorize the secant term, and we're left with tan x plus secant x, and that's over secant x plus tan x. What you now notice is, well, these two are the same term, so we can reduce it or cancel it, and we're left with just secant x, which is the original integral we wanted, okay? So the integral of secant x is just ln secant x plus tan x plus c. Okay, so the last one I'm going to do is this cosecant x, okay? So this is another tricky one, so we're going to let y equal to the natural log of cosecant x plus cot x. If we differentiate this, we would get cosecant x plus cot x in the denominator. Differentiating cosecant x, we get minus cosecant x cot x. And differentiating this cot x, we get negative cosecant squared x. If we were to go about now factorizing the numerator, taking the cosecant out, or let's take the negative out as well, so negative cosecant x out, we'll be left with cot x plus cosec x. Okay, and that's all over cosec x plus cot x. You can see that now that these two terms can cancel, and we're left with negative cosecant x. Okay, so if we could compare this term with the original integral, well, the only difference is this negative sign. So this is going to be equal to negative our y value, which is ln cosec x, sorry, I'm going to write it underneath, plus cotx. Okay, so this secant x and cosecant x integrals are very tricky to see or identify straight away, but this is how you go about proving it. Right, and the last one I want to do is this 4 raised to the power of 3x, okay? This is another way, or we use the reverse chain rule for this as well, okay? So what we do is we let y equal to 4 to the power of 3x, the same thing, okay? Because we can now differentiate this. Hopefully we can differentiate this. The way we go about differentiating, well, let's write this in terms of e, or exponential. We can write it as e raised to the power of ln 4 to the 3x. Because these two terms will cancel out and we're left, it's the same thing. The reason why we do this is because we know how to differentiate exponential terms, okay? So it's a bit easier for us. So if I were to rewrite this as well, e, and using the power rule, or one of the log rules, we can bring this 3x to the front. So it's going to be 3x ln 4. Now we can go about differentiating the exponential term, because we can differentiate this power, or the raised power term here, and that's going to leave us with 3 ln 4, and we're going to have e to the power of 3x ln 4. This I can simplify a bit more. We're going to have 3 ln 4 e to the ln 4 to the power of 3x. These two terms will cancel out and we're left with 4 to the power of 3x times 3 ln 4. Okay, so this is how you go about differentiating this kind of term. We now compare our dy by dx term with this original integral, and as you can see, it's just this 3 ln 4. Don't be scared of this value. It's just a constant value like any other number. And so what we can say, this is equal to 1 over that number, which you would want to get rid of. So it's 3 ln 4 multiplied by our y term. So it's going to be 4 to the power of 3x plus c. Okay, so it might look a bit tricky in the beginning, but if you go step by step, then we can clearly see that this will be this term here. All right, the integration by trigonometry and substitution, I will go through in the second part of the video.